Good afternoon. I hope you had a good lunch. So for this presentation, I will discuss how site-specific simulated ground motions from SGMD can be used to assess and enhance our confidence in seismic resilience. Again, Dr. Salim Gunai was a key person in developing this work, in addition to several peer and CE lab staff that they were involved in different aspects of this project. The presentation focuses on the so-called Grimes Engineering Center. For those who haven't been in the Berkeley campus, this is what used to be the Bechtel Engineering Center. Now it's called the Grimes Engineering Center at UC Berkeley, and it's as a demonstration project linking physics-based simulation, resilient structure design, laboratory and field testing, and regional scale seismic assessment. A major theme throughout this talk is that SGMD allows us to move from generic seismic assessment toward geographically consistent scenario-specific resilience evaluation, analogous to what I presented earlier for BART. So this presentation is a little bit dense because it intentionally spans multiple scales and topics. I will begin with Grimes Center as a building scale demonstration of resilient design and site-specific SGMD applications, then transition into comparisons between SGMD and code-based spectra, and finally conclude with a broader potential of SGMD for regional scale resilience assessment and earthquake sequence simulations. That's more of just provoking discussion that can come in the panel discussion later on tomorrow. The talk is organized into three parts. First, I will discuss what SGMD enables conceptually. Second, I will present the Grimes Engineering Center as a case study demonstration. Finally, I will discuss broader regional implications and the future directions. This statement here captures the central idea of the presentation. Traditionally, seismic design often relies on generalized spectra, amplitude-scaled records, and ergodic assumptions. SGMD enables something fundamentally different, that is site-specific, scenario-consistent, physics-based assessment. The Grimes Center provides a real-world demonstration of how this framework can support resilient design and assessment. The important shift is that resilience can now be evaluated using motions tied to actual faults, realistic rupture scenarios, and local site conditions. One major strength of SGMD is that it bridges multiple scales. At one extreme, we have regional scale hazard affecting millions of buildings. At the other extreme, building-specific response and condition assessment can take place. The Grimes Center is located near a specific SGMD site, this site 2020, in Berkeley, and similar to BART study that I presented earlier, this creates a near collocated relationship between the actual structure and the simulated hazard environment. This is important because it allows the building assessment to remain geographically meaningful rather than relying on generic motions selected from unrelated locations. The Grimes Engineering Center, for those who do not know, is intended to function as a living lab for resilient design. The project is not simply a design exercise nor an experimental study. I overlook to acknowledge the SOM engineers who are the designers of the building that we worked very closely with them. It's actually not design of a building, it's design of the modified building because it's the Grimes Center is built on the old Bechtel Center. So SOM were the designers and the ones we worked with closely on this project. So as I said, this project is not simply a design exercise nor an experimental study. Instead, it creates a closed loop framework: design, test, validate, and improve. Or at least improve in the sense of better understanding of the functionality, the recovery potential following an earthquake. The building is less than quarter mile from Hayward Fault, so earthquakes are going to happen, and we're going to see data and results and response. The building integrates advanced systems, sensing experiments that took place prior to completing the design, and physics-based simulations. This type of integrated workflow is increasingly important for resilience-oriented infrastructure. The Grimes Center was specifically designed for resilience, rapid recovery, and immediate occupancy after earthquakes. This represents a major shift from traditional collapse prevention philosophy. The objective is not simply to prevent collapse. The objective is functionality, operational continuity, and minimizing downtime. This becomes essential for critical facilities, research buildings, and community infrastructure. This slide here shows, this is from SOM, shows the evolution of the structural system. The design progressed through several stages, starting from existing condition, adding buckling restrained braces, interior frames, adding new levels, incorporating shape memory alloy perimeter frames, and ultimately adding the roof structure. Two key systems are central here. First is the buckling restrained braces, or BRBs, which provide ductility, stable hysteretic behavior, and energy dissipation. Second is the shape memory alloy systems, which provide recentering, residual drift reduction, and additional damping. The combination allows the structure to dissipate energy while also limiting permanent deformation. This is a summary of the benefits observed from the SMA system. You see here some of the experimental results that show the recentering capability. And the SMA are these cables you see on top here of this tension rod that go all around the perimeter of the building. So compared to conventional tension rod system, peak drift was reduced by introducing the SMA rods. Residual drift was reduced substantially, torsion decreased, and floor accelerations were lowered. And that's important. The building houses this artwork that's called the Cube, which has thousands of LED lights which serve a particular educational function, which I don't have time to explore today. So it was important to pay attention to that and to have the floor acceleration being lowered, which is very important for functional recovery and so on. The residual drift reduction is particularly important for functional recovery in addition to reduction of the floor acceleration. Many buildings survive earthquake structurally, but become unusable because of excessive residual deformation. Reducing residual drift directly improves repairability, reoccupancy, and ultimately resilience. This is one of the strongest motivations for advanced resilience systems. This slide here emphasizes the integrated framework behind the project. The Grimes Center combines architecture design, which was led by SOM, laboratory experiment that Peer and CEE Structure Lab were involved in, analytical simulation, and condition assessment using field testing and monitoring. This includes shaken table testing, SMA component, and the frame tests. I showed you the hysteretic response for it in the previous slide, and field measurements. The important idea is that resilience assessment should not rely on a single methodology. Instead, resilient design increasingly requires integration across experiment, simulation, sensing, and operational monitoring. Here is a summary of the field testing, also using Peer Sense that I mentioned when I talked about the bar tests. And here we used an eccentric mass shaker to excite the building after it was constructed. The objective was to identify modal properties, natural frequency, and validate analytical model. And results were very promising. The measured response showed good agreement with analytical predictions done by SOM engineers. So you see here this table. The field validation is critical for digital twin concepts and longevity of this monitoring and continue learning from this living lab, and of course for resilience-oriented assessment. Here we compare the Grimes Center location with the closest SGMD site that we have in the Peer data set, Peer LBNL data set. Of course, LBNL has a lot more finer grid, but our grid currently is the 2-kilometer grid. So the closest one was this station in the central Berkeley that we made use of. This is sufficiently close for building level assessment. As I mentioned, the building is less than a quarter mile from Hayward Fault, as you see here. The motions, therefore, that we use to preserve local site effects, source to site geometry, and the near fault characteristics. This allows SGMD to support, as I mentioned, non-ergodic, geologically meaningful site-specific assessment. Here we compare SGMD spectra with code-based design and maximum considered earthquake response spectra. An important observation is that some individual motions, here we see the 50 realization in gray, and then see mean plus standard deviation compared to the code. So we see some individual motions exceed MCER near the dominant structure period, which is around in the vicinity of 0.6 to 0.8 second. I think it shows in a later, yeah, it shows the range here. While the median behavior aligns well with the code spectra. One thing, at longer periods, the motions fall below the design spectrum. Why is that? Because code spectra reflect contributions from multiple faults, multiple magnitudes, and the probabilistic hazard aggregation. The SGMD motions here represent a specific magnitude 7 Hayward scenario. Another important point is the influence of near fault directivity and super shear rupture effects that David mentioned in the morning session, which can amplify long period response. We expect very soon to add more data in the SGMD that would address this issue more properly. This slide shows one explanation of one of the reasons that the code include more than just one fault, more than just one earthquake scenario. So this slide shows the de-aggregation of the hazard supporting the previous observation regarding code versus SGMD comparison for long period spectral value. So this for short period, which you see the magnitude 7 is equally dominating as the higher magnitudes, but this relative contribution reduces when we start looking at a longer period structures here. So that explain that observation. So a provoking question here, do we still need to artificially modify, scale, spectrally match, or some shape matching motions to match code spectra? Something to think about and discuss in the coming panel discussion tomorrow. Clearly, SGMD provides scenario-consistent motions tied to realistic rupture physics without artificial modification. This is an important conceptual shift. The motions are not intended to create an artificial envelope. Whether this is still needed or not, I think it's worthy of its discussion. The motion represent a physically plausible earthquake scenarios. This may ultimately support more realistic, resilient assessment. But what do we do about addressing the differences with code spectra, and what would engineers be comfortable with? So I think that I'm just pausing this here as a point of discussion for tomorrow. This slide shows directional effects. The expected near fault hierarchy appears clearly where rod D100, then fault normal, then rod D50, then fault parallel. So this behavior is physically consistent with near fault directivity. An interesting observation from this exercise is that rod D50 exhibits smaller dispersion because it represents the median across many rotated orientations. So these directional effects are extremely important for tall buildings, torsional systems. Torsion was an issue for this building, so it was important to look at that, and pulse-sensitive structures, as we heard in the morning. As part of this exercise, also we examine pulse periods and spectral velocity behavior. The pulse period is close to the natural period range of the Grimes center. This was obtained with wavelets. This is important because when pulse period approaches structural period, demand amplification can become significant, and we had a discussion about that in the morning. This is one of the major concerns for near-fault structures. The slide also illustrates the increasing dispersion at longer periods, which also related to what I mentioned earlier. One important thing we went through is shown in this slide, which is particularly important because resilience is often governed by non-structural systems. The hypercube LAD installation in the Grimes Center was evaluated probabilistically using the ASCE7 equation to estimate the floor, peak floor acceleration. The calculated demand probability was very low, which is encouraging because the collapse prevention alone does not guarantee functionality. Many resilience failures originate from non-structural damage. This is where SGMD becomes especially powerful probabilistic assessment of non-structural performance under geographically realistic motions. This is now a look into the future, what SGMD can offer. I'll do this quickly, I'm running out of time. So here we expand the discussion to regional scale assessment The scenario involves, yes, the music means I should stop. I'll take one more minute and then
No,
I
no, please
finish.
go on, go on. Yeah, it's
Okay.
automated thing. Yeah.
Okay, so the scenario involves a Hayward main shock followed by a Calaveras event. The same thing we did also for the BART, consistent with ETAS sequence concepts. So this demonstrates how SGMD might be able to eventually support earthquake sequence simulation, cascading hazard assessment, and regional resilience evaluation. So this is part of a project we have. Selim is leading it from Cal OES, where this slide shows regional scale damage assessment involving approximately 4 million buildings. The maps illustrate how damage evolves after sequential events. We work with USGS for this data set that I showed in the previous slide. This is not using SGMD, but this is a potentially possible using SGMD data in the near future. So this has one main shock, magnitude 7.2 in Hayward, followed by a second main shock, magnitude 7.2 in Calaveras. And the map show how damage evolve after this sequence. This demonstrates how SGMD could be used in the future for a study like this, going at different scale from a single building to entire metropolitan region. This is particularly important for resilience planning, emergency response, infrastructure prioritization. This will emphasize, or I'm putting this here to emphasize discussion for future directions that SGMD may be interested in looking into ETAS-based sequence scenarios, multi-event hazard chains, and regional resilience simulation, which is very important if we are going to speak about digital twins of cities, operational decision-making, and infrastructure risk management. If you look carefully, you see here, for example, a lot of the blue points become green when the second main shock is applied. So that would be another thing to consider for future discussion. So to conclude, SGMD provides site-specific, scenario-consistent, physics-based ground motion. It enables assessment without relying entirely on artificial spectral matching. It supports structural systems, non-structural systems, single building analysis, and hopefully eventually regional scale resilience assessment. And we saw some of that already. Most importantly, SGMD is not simply a database. It represents a fundamentally new paradigm for seismic design, resilience assessment, and the future infrastructure decision making. Thank you very much.